Hello, my name is Liam Duncan, and I am a junior majoring in wind energy and minoring in atmospheric science. Today, I will be discussing my research on testing the accuracy of the Purple Air PA2 sensor. This sensor is a low-cost sensor that measures particulate matter in the air, particularly particulate matter of the sizes smaller than 2.5 micrometers and 10 micrometers. So first of all, let's discuss what particulate matter actually is. Particulate matter is microscopic particles of solid or liquid matter suspended in the air. Common types of particulate matter include the likes of soot, smog, ash, dust, and even biological or organic components that include viruses, bacteria, mold spores, and pollen. These can all range in size from 1,000 micrometers all the way down to 0.0001 micrometers. So why do we measure particulate matter? Well, atmospheric particulate matter is one of the leading causes for the global burden of disease. On top of that, in the United States, 3 to 5% of annual deaths are attributed to particulate matter of the size 2.5 micrometers or smaller. This is due to the fact that these size of particles can penetrate deep into the lungs and even into the bloodstream if they're small enough. Measuring these particles becomes particularly important when certain natural events occur, like dust storms and also wildfires. This data was taken from a wildfire that occurred in California in November of 2018, and it shows a high spike in the daily average of particulate matter in that area. This is very unhealthy for residents in this area, and it's important to know that this is occurring. So let's take a look at what is most commonly used to measure particulate matter across the United States. So this is a particulate matter sensor located in Lubbock, and it's owned and operated by the Texas Commission on Environmental Quality. Now, this is how we traditionally measure particulate matter in the United States, the only issue being that they are extremely expensive and only exist in large cities, leaving large swaths of land where we can't measure data. That's where the Purple Air has a great advantage over it. There are over 10,000 Purple Air sensors that we have counted so far in the world, a majority of these being in the United States. That being said, our Purple Air sensor that we have is private, so it's not visible on the map. So we believe that there are more than 10,000 sensors out there. With this sensor coming in at around $250, this is significantly cheaper than any of the EPA sensors that are currently in place. We also hope that it can be used to fill in the gaps between the only 220 EPA sensors that currently exist in the United States. Let's talk about the architecture of the Purple Air. So the Purple Air is actually two sensors that take measurements of the same thing and then cross-reference their measurements. It does this by this diagram right here shows the particles flowing through a laser, and the particles scatter the laser, and then the laser scattering is measured by a receiver, and that's how it determines the size and the amount of the particles. So to actually test the accuracy of the Purple Air sensor, we will be comparing the measurements that it takes to the TCEQ station as well as our own aerosol research observation station. The Aero station has various instruments that measure different types of aerosol in the atmosphere. The reason we are using this as well as the TCEQ sensor is because the Purple Air sensor is co-located to the Aeros, whereas the TCEQ sensor is approximately 5.1 miles away. This is important because particulate matter can vary greatly in short amount of distances, and co-location is really important when measuring these types of aerosols. The specific instrument that we use to compare against the Purple Air is called a portable aerosol spectrometer, or the GRIM 11D. This works by measuring the scattered light from a particle. So when a particle passes through the laser beam, it is illuminated. This results in scattered light. The scattered light is directed via a wide-range optical system to a receiver diode. Now I'm going to discuss how we cleaned our data. The Purple Air sensor was cleaned, not corrected, And so we average sensor A and B together on the purple air. As shown here and discussed earlier, there are two sensors on the purple air labeled A and B, both collecting data. And by averaging them, you get a cleaner view of the data. We also cleaned extraneous data like negatives and values larger than 200, as that is extremely uncommon. The TCEQ sensor is cleaned and corrected by both the Texas Commission on Environmental Quality and the EPA. And our GRIM sensor was cleaned and only corrected for removing the silica particulate from the dryer above the sensor to ensure that that was not skewing our data. We also removed days with less than 12 hours of data, as that causes some extraneous data points. So we're going to start our data results off with the hourly comparison of the purple air PA2 sensor and the TCEQ sensor. This is going to be the hourly averages of the PM 2.5 concentration. For all of our data, purple air will be represented in orange, TCEQ will be in blue, and later on the arrows will be represented in green. As we see, the purple air is pretty much consistently over the TCEQ in terms of measurements. And we had a total of 12,540 hours measured from March of 2019 to October 1st of 2020. And the purple air measurements added up to 12,792 hours of data. Moving on to our daily averages of PM 2.5 for the purple air and the TCEQ. This one's a little bit easier to read, and it shows again that the purple air is consistently overshooting its measurements compared to the TCEQ. This is the same time scale as the hourly, and we had a total of 541 days for the TCEQ and 538 days for the purple air sensor. Moving on to the regression graphs, this is where we see the greatest discrepancies from the TCEQ measurements and the purple air measurements. If these measurements were the same, it would follow the one-to-one line displayed here as the dashed line. The dotted line is the linear line of best fit for the data, and up here is our R-squared value, which was 0.39 for our daily values and 0.21 for our hourly values. This shows that the data is very inconsistent and that the purple air is, in fact, not as accurate as the TCEQ. Comparing the hourly graph to the daily graph, we see that our R-squared value does increase from hourly to daily, and you will see this trend through all of our regression graphs to come. Another way to visualize our data is a box and whisker graph. This shows a statistical distribution of our data, both for the purple air and the TCEQ. So the box, it represents, the line in the middle represents the median of the data. The lower line is the lower quartile, the upper line is the upper quartile, and then the X is the mean. And the top of the whiskers and the bottom of the whiskers represent the maximum, the minimum, and any remaining points are considered outliers to be outside of the data. In a perfect scenario where both of these sensors were recording the same data, the box and whiskers would all be in the same place, and the amount of outliers would all match up. It's also important to note that we do not expect the TCEQ and purple air sensor measurements to be exactly the same, considering they are 5.1 miles away from each other. So we're keeping that in mind when comparing the TCEQ data to the purple air data. Next, we're going to move on to our comparison of the purple air sensor and the aero sensor. So here we have our hourly comparison of particulate matter of 2.5 microns or smaller concentrations. This timescale is a little bit different than the one for the TCEQ sensor. This is from March 2019 to March 2020, so 1 year. Here, again, we see that the data is a little bit closer to the purple air is a little bit closer to the Aeros data than it was to the TCEQ data, but yet again, we still have large discrepancies in the data, specifically with the purple air overshooting compared to that of our Aeros sensor. The total hourly Aeros measurements added up to 6,411 hours, and the purple air measurements added up to 8,264 hours. Moving on to our daily comparisons of purple air sensors and the Aeros sensor. Here again, the data is a little bit easier to read. We again see that the purple air sensor is overshooting the Eros sensor, and the total daily Eros averages added up to 279 days, and the purple air averages added up to 349 days. Looking at the regression graphs comparing the purple air sensor and the Eros sensor, we see that the data is actually a little bit better than that of the TCEQ. This is expected considering that these sensors are co-located and not 5 miles apart. Again, we have a low R-squared for both of these, and again, we have an increase from our hourly values to our daily values, and we expect that. Reinforcing the importance of collocation, we see that the Eros and purple air data in our box and whiskers graphs also improve compared to that of our TCEQ and purple air data. And we see that the boxes are closer together and that the medians and averages are closer as well. So one thing that we can compare with the Eros sensor and the purple air that we can't with the TCEQ is particulate matter 10. The TCEQ, the Texas Commission on Environmental Quality, doesn't release and doesn't have a sensor for measuring particulate matter of a size 10 microns or smaller. But our Eros does. So when comparing that, it kind of flips everything we thought we knew about the purple air sensor on its head. Here we see that the Eros is consistently overshooting the purple air when it comes to particulate matter concentrations. Similar here, but also in the months of like November and December, we see that the purple air sensor is higher than that of the Eros sensor. So seems to be a lot of discrepancies with our purple air measurements. For these hourly measurements, we have 6,407 hours for Eros and 8,262 measurements for the purple air. Looking at our daily, we see this again. Similar to our hourly, Eros consistently overshooting purple air, and yeah, we have our Eros averages. We have 279 days for that and 349 days for the purple air. Moving on to our regression graphs, this is consistent with the data that we saw just a couple slides ago. This is pretty bad. We have R squareds, less than 0.2, which is really low, and also our linear fit skews hard for Eros, showing that the purple air is consistently under measuring what the PM10 should be. Moving on to our box and whisker, these show that the Eros is consistently higher than the purple air as shown earlier. And here we also see that in our hourly. So obviously PM10 not the best for purple air. In conclusion, the purple air sensor is not a viable sensor for research applications given that the R-squared values of the linear line of best fit are too low. They do not match the measurements of actual professional sensors like they should. That doesn't mean that they are useless, as they have a potential to fill in gaps where EPA stations do not exist, as we have shown earlier with the purple air map. With that being said, I think these sensors could provide a better solution for those in high-risk groups and those who suffer from the likes of asthma and everything else, especially as these events like wildfires and dust storms become more frequent and intense due to climate change. Thank you for watching my presentation. I'd also like to thank Dr. Ardon Dreyer and the Center for Transformative Undergraduate Experiences for this great opportunity.